Quantum entanglement is a phenomenon found in quantum mechanics that defies our intuitions about correlation and causality. In this video, I will attempt to explain the phenomenon and its implications for our understanding of the relationship between correlation and causality. Two particles, A and B, may be produced in the same event and then move away from each other, but still be in a sort of relationship called entanglement. Quantum particles have a property called spin, which may be thought of as a particle rotating. A particle may have positive or negative spin in a given direction, which we will portray as spinning clockwise or anti-clockwise. When two particles are entangled, they will have opposite spins. This relationship will hold even if the particles are separated by a large distance. A particle's spin may be measured in multiple directions, giving different values for the spin. When entangled particles A and B are measured in the same direction, they will have opposite spins. Because of this, we say that the spins of A and B measured in the same direction are correlated, meaning that knowing one will tell you information about the other. However, no such relationship need hold when they are measured from different directions. It is well known that correlation does not imply causation, but in everyday life it seems that correlated variables fall into one of four categories, as summarised in this text from Wikipedia. The four possible relationships given here are that A causes B, direct causation, B causes A, reverse causation, that A and B are both caused by a common variable C, which is called common causation, and then the fourth option being that there is no connection between A and B and the correlation is a coincidence. So which category does this correlation that we have identified in quantum entanglement fall into? Well, for a start, it seems that we can rule out coincidence because there have been an enormous number of experiments performed on entangled particles, and the relationship has been consistently observed. If it were a simple coincidence, then we would expect the relationship to go away after repeating the experiment multiple times. Perhaps the measurement at A affects the measurement at B, or vice versa. Well, according to Einstein's theory of relativity, information cannot flow faster than the speed of light. This speed limit doesn't just apply to particles, but to the flow of information itself. So if the measurements at A and B occur very close together, then even if they occur at slightly different times, as long as the particles are so far apart that not even a beam of light could have communicated the information because it wouldn't have had enough time, then we can rule out these two options as well. So in conclusion, it must have been the third option, and the measurements at A and B must have a common cause C, right? Well, surprisingly, the answer seems to be no. Imagine that A and B move apart from each other after they are created at close to the speed of light. Then, in order for the information at C to get to A and B in time for the measurements to happen, the event C must have happened not long after A and B were created. So in this animation, particle C disappears because the common cause, if one exists, must have happened close to the time that A and B were created. This means that, assuming the common cause hypothesis is true, the measurements of the spins of A and B in a given direction must depend on factors that were already determined shortly after the creation of A and B. So, for example, the spin in the upward direction must be a property of A that already exists and is simply waiting to be measured. And similarly for B. We might metaphorically say that the particles have already decided what their spins will be if measured in any given direction. The following argument is known as Bell's theorem and was stated by John Stuart Bell in 1964. Suppose that we label these directions, as shown in this diagram, as 1, 2, 3, and 4, and we repeat an experiment with many pairs of entangled particles in which we randomly choose directions to measure the spins of A and B. Our algorithm is as follows. We choose a random direction, either direction 1 or direction 2, in which to measure A. We then choose independently a random direction, so either direction 3 or 4, in which to measure B. If A and B are spinning in the same direction, we say the outcome of the experiment is 1. And if they're spinning in opposite directions, we say the outcome of the experiment is -1. However, if we randomly chose direction 2 and direction 4, then we change the outcome to be the opposite of what it would otherwise have been. So if it was 1, then we change it to -1, and if it was -1, then we change it to 1. If, as we assumed, the outcomes of the measurements are predetermined, then for any pair of entangled particles, we can write the spins that they will have in the given direction. So we can write A1, for example, to be the spin that particle A will have if measured in direction 1, and similarly for the rest. We calculate the following inequality, that A1B3 plus A2B3 plus A1B4 minus A2B4 is less than or equal to 2 for all choices of A1, A2, B3 and B4, and hence the mean outcome can be no more than a half. And you can verify this for yourself by just plugging in plus or minus 1 for all of the different possible values. And when I say the mean outcome can be no more than 1/2, what I mean is that because our experiment is to choose a random one of these 4 terms to measure, and the sum of them all is less than or equal to 2, on average, we will get something that's no more than a half. However, quantum theory predicts that the expected value of AI times Bj is equal to minus Vi dot Vj, so dot being the dot product and Vi and Vj being unit vectors in the directions I and j, respectively. In the example that we gave at the beginning, so all relevant angles are either 90 degrees or 45 degrees, this gives a mean outcome of 1 over the square root of 2, which is greater than a half. And this is in line with observations that have been made of real particles. So this means that our hypothesis that the measurements at A and B are both caused by some common factor C must in fact be wrong. So we reject this hypothesis. So apparently we have ruled out all possible reasons for correlation, and yet A and B is still correlated. So how can we explain this? Well, notice that all of the options in this list, apart from the one that appeals to random chance alone, involve some sort of causation. What does causation really mean? Well, for a start, it is necessarily time dependent, because the cause has to precede the effect in any causal relationship. As shown in these 3 diagrams, all 3 options rely on events happening at different points in time. But correlation, as a mathematical property, is a symmetrical relationship, which means that for any 2 variables, x and y, if x is correlated with y, then y is correlated with x. There doesn't seem to be any order to this necessarily. And perhaps more importantly, the relationship may be defined independently of time. It's not a particularly special property. It just means that the mean of x times y is not equal to the mean of x multiplied by the mean of y. In fact, it's arguably more noteworthy if 2 variables are not correlated. And importantly, there is no a priori reason for any temporal relationship to be involved. So maybe these four options that seem to account for any correlation are the equivalent of a false dichotomy, which for four options is called a false tetrachotomy.